Okay, so I'm going to talk about a subject which actually started during the summer school of 2001. I was then giving a talk on extreme wave events, and slowly I started to realize how I could go about this subject and what to do in the context of operational wave forecasting. You should realize I'm doing very basic things in my work, providing software, running automatically, etc. And I'm trying to pull in as much science as possible to make it a fancy system. And I thought that attempting to do freak wave forecasting would be a nice thing to do. Also quite controversial, because I can tell you my predecessors are dead against this. Yeah, they think it's all nonsense. Okay, so during that work on the freak waves, I realized that I had to think a little bit about random time series analysis. And so this is the main subject of the last part of my talk. But I first will try to give you a bit of information on how to get around the probability of occurrence of extreme events or freak waves. People call it freak waves, rogue waves, but that's just a matter of taste. And I've written that up in a tech memo. If you go to our website, you can just find all the details, which of course I won't give today. So this is an example of a freak wave event. It's we call it the Draupner wave. It's, I believe, 1st of January 1995. And as you can see, I hope this works. Well, I just walk. No, that's why I'm a bit nervous. So this is a freak wave. You know, the typical wave height of this time series is
the technological.
Yeah, okay, yeah, I like this. Yeah, but that's too difficult for me. So the average wave height of this time series is about 12 meters, and wave height is the distance from crest to trough. And here you see this exceptional wave, which has a wave height of about 26 meters. So that's quite exceptional. You know, the ratio of the wave height of the event over the background larger than 2 is already regarded as an exceptional event. So, and this is, one of the first times we really recorded that in such explicit fashion. Before that, this was done by using a laser. Usually we are measuring waves with a wave buoy, and when those events happen, we just disregard the record, because this is so outlandish, you can't believe that. So then it was assumed that the buoy was not functioning properly. Yeah? So until people started giving pictures of how it could happen that this extreme event occurs, and then they started retaining the records, or in fact, most people retain the records, of course, and then looked at it, and we have seen, quite a few examples of extreme events of this type. Yeah.
So I have a suggestion for measurement, because this, of course, is one device looking down, but if there were 3 devices on that platform,
yeah.
spaced several
yeah.
tens of meters, say, away, then we could get velocity
yes.
and
yes.
information. This
yes.
only tells
yes.
us
yes.
one.
Yeah, that's certainly
needed.
Wouldn't be that
more expensive, would it?
No, not really. No, that would work much better, because of course we can't really explain this time series event because it's 1D. Yeah? It's not enough.
Not quite enough. It's still interesting.
But in the platform, there are already 5 lasers. They're looking not at this time, but now that they're
nowadays,
they have
yeah.
5 lasers working.
Good.
Yeah. But this one we can't explain really. Huh? There are a few questions. For instance, with the event associated a wave setup, usually you would expect a wave set down due to a wave group. But in this case, it's a setup, and lots of works have been devoted to trying to explain the reasons for this.
Well, it could be a directional thing.
Yeah, it is a directional thing, probably.
And 3 is enough.
Well, I would do a bit more. I know that Paul, there's this idea that if you just have 3 wave stars, then you can do the directional spectrum. But it turns out that you need a fair bit of more to do it accurately. Okay, in principle you can get that information, but maybe it's better to have 40.
Yeah.
According to Paul Horn. Okay?
Probably not that much more expensive either.
No. Certainly nowadays. So this is an example of a freak wave event. As you can, I like this picture very much. First of all, because of the shape of this event. This can be obtained from numerical simulations of the exact equations right away. The other thing what I like is, as you can see, it's fairly light. So this is an event that has nothing to do with the actual weather. It is really internally generated by the dynamics of the waves. And of course those events can be quite extreme, and of course that also results in damage. This is caused by freak waves in the Agulhas current, and as you can see they easily manage to make big holes in ships, and for this reason we have to be careful, of course. Okay, so that's just about freak waves. Good morning. What I will do today is I will briefly review freak wave theory. I will go in a very quick fashion through it. Then I will start looking at the subject I really want to talk about, is namely, of course it's nice to have a theory on extreme events, but if you want to compare that with observations, you need to be able to compare like for like. And in oceanography, the tradition has always been to look at wave heights, to look at wave height distribution, maximum wave height distribution. But if you look at that approach, it's very difficult for a theorist like me to make a theory on this. Because what is wave height defined in this case? You just have your time series and you have your zero line. You take an upcrossing and you take the next upcrossing. You then take in that domain a maximum and minimum, and you derive wave height from that. But of course that's a very discrete method of doing measuring an extreme event. So I'm much more interested in things like the envelope of a wave train, because the envelope square is basically the power of the signal, and you can do much more with that approach, because it's of course continuous. You measure it all the time. Yes.
Tell me about the envelope in the previous slide.
The previous slide, yeah.
Oh, sorry, the drop
Time series.
Oh, sorry, yeah, wait. This one.
Yeah, tell me about the envelope.
Yeah, so I need to have the Hilbert transform from this and then square it, but I think it's just going along the points here, yeah? Isn't it? So that's the envelope.
So if we leave out the Druckner wave and look at only at the left or the right, then it's maybe a little more clear, right? I think Harvey's worrying about that.
But
Well,
why are you asking this, Harvey? Because
because
you know it by heart that this is the envelope.
Yeah, but it's not clear that the envelope has any relevance. The idea of an envelope has any relevance for that particular wave, because there's just one.
Well, it's a very steep envelope.
Steep envelope.
Yeah, that's all right.
Okay.
Let me explain. I mean, I'm not the only one who's come up with this idea. I mean, Rice in 45, Gabor in 46, they are all suggesting this already, and they come up with a method which is based on the Hilbert transform. And I can tell you the method has also been applied in oceanography by Ken Melville in the early 80s, and it works very well. It's just used as a way to characterize an extreme event to get really a decent measure of it. Yeah.
Just can I make a comment, Harvey? There is no need, when you use Hilbert transform, there is no need of narrow band approximation. Okay, Hilbert transform is free of
It
that.
also, and I will show you that in the rest. Okay, so and then I also show how that it is straightforward to extend this to nonlinear waves, because I will show explicitly that it works for linear waves, and then I'll sketch how to go for nonlinear waves. Okay, so first the well, I call it freak wave theory, but it's just basic surface gravity wave theory. So the starting point is the Hamiltonian for surface gravity waves. What is important is that there is no knowledge of the phases of the waves, therefore I follow a statistical approach, and I mean no knowledge of the phase of the waves in practice. Then using perturbation methods, I derive an evolution equation for the action density and obtain an expression for the kurtosis of the sea state, which is a good indicator for extreme events, as we will see. And the simplified theory is then, for a special simplified spectrum, I compare with laboratory data. So first, those things about Hamiltonian theory, etc., you all know, so I will go very quickly through it. So the Hamiltonian is just a sum of kinetic and potential energy, and it's a conserved quantity, because we have potential theory. So we choose eta and psi, which is the velocity potential at the surface, as canonical variables, and then Sakharov realized that the kinematic boundary condition and Bernoulli's equation are just Hamilton's equations given over here. This is the kinematic boundary condition, this is Bernoulli. And this derivative is the usual functional derivative with respect to psi. Okay, so that's a problem, and then we have to supplement that with the potential equation for inside the fluid. So we have Laplace's equation for the potential, and we have boundary conditions that the potential at the surface is psi, and we have some sort of no penetration of fluid at the bottom. Now, by solving the potential problem, at least in your head, we can do that. Then phi may be expressed in terms of the canonical variables eta and psi, and then the energy may be evaluated in terms of the canonical variables, and the evolution in time of eta and phi follows at once from Hamilton's equations. Now, for the point to note is that for small wave steepness epsilon, the potential problem given here may be solved in an iterative fashion. And in order to do that, Sakharov introduced the Fourier transform of the surface elevation, denoted by eta hat. And we also need the dispersion relation for linear waves, as given over here. And then you realize that there are basically two modes, one going to the right and one going to the left, and then you introduce an action density in the following manner. So eta hat is given by the sum of this, and psi is the difference of this, involving also a factor of I. So this is the action variable, capital A. And then if you do the work, you will find that the energy of the waves is just a series expansion with quadratic terms, which corresponds to linear theory, cubic terms corresponding to three-wave interaction, quartic terms corresponding to four-wave interactions, and etc., etc. And then, of course, we know that for surface gravity waves, there are no resonant three-wave interactions, and so that means that you can introduce a canonical transformation of the following type, which is non-singular, which then removes all the non-resonant third and fourth order terms as much as possible. And then this small a is actually the amplitude of the free waves, and the canonical transformation is just used to separate free waves and bound waves. And so for the good part of this talk, I will only talk about the free waves, but the bound waves are also relevant for estimating kurtosis, by the way, because if you have sharp crests and wide troughs, that gives also deviations from the probability distribution function. Right, so then you apply the work of Krasicki, because he actually worked it out correctly, and you get a Hamiltonian that looks like this. It only contains quadratic term and one type of quartic term. And the interaction coefficient T of the matrix is very complicated, of course, but it has a number of nice symmetries, and the most important one is this one, because this ensures that the system is still Hamiltonian. And then if you apply Hamilton's equation to this energy, then you will obtain the well-known Zakharov equation, which is given over here. So it's a very simple looking equation. And it involves, this is the condition for resonance in wave number space. But there's no condition imposed on resonance in frequency yet. So this Zakharov equation describes 4 wave interactions. They are given over here. It's this type of resonant interaction. And many, many properties of the Zakharov equation have been studied. But I won't discuss that in full detail at all, of course, because I don't have the time. I only discuss briefly the connection between 4-wave interaction and nonlinear focusing in a very simple way. Because what actually happens is that this evolution equation, if you apply it to the problem of the stability of an envelope wave train, then you will get under certain conditions an instability, which we call modulational instability, Benjamin-Fair instability. Now, this Benjamin-Fair instability is basically a competition between the dispersion of the waves and the effect of a nonlinearity giving focusing. And in a one-dimensional setting, where you only have a frequency spectrum, then this balance can be expressed by means of the so-called Benjamin-Fair index, which is basically the ratio of the steepness of the waves over the relative frequency width. And I've defined those quantities over here. And eta square average is the variance of the sea surface. Okay then, so this is in 1D. But in 2D, things are slightly more complicated because due to the finite directional width of the spectrum, there's a considerable reduction of the instability. And this effect is measured by this parameter, which is the ratio of the directional width over the frequency width square over 1/2. But 1/2 is introduced in such a way, it turns out that for r equals 1, nothing happens for narrowband waves. Now, and I can argue this, of course, those two parameters are not really quite, not strictly relevant for the Zakharov equation, but in the context of a narrowband wave stream, they are. Because then they are the only two parameters which are relevant for solving the NLS equation for a spectrum of waves in an ensemble context. These are the only two parameters that matter. So these parameters I'm going to use later on. Okay, so this is to show that we have focusing. This is Benjamin-Fair instability. This is a wave tank time series. This is close to the wave maker. This is far from the wave maker. And you see you start with a uniform wave train, and after a while you get strong modulations, and therefore these are what we would call freak wave events. Yeah, so that's the focusing, and that focusing mechanism is completely determined by something like the steepness over the width of the spectrum. And here I have the sketch of the definition of the Benjamin-Fair index. So we have a spectrum of looking, say, like this in frequency space. Then this is the width, it's actually the half width, and the height is basically proportional to the steepness square. Okay, so then the possible generation mechanism for extreme events, at least on the open ocean when we have no currents, is basically the following. They are generated by a combination of luck, for instance, constructive interference, which is then followed by nonlinear focusing, because then you trigger steeper waves, and then the Benjamin-Fair type of instability process can start to act. So this is this was a proposal for a generation of freak waves on the open ocean some years ago. But as you can see, you know, this mechanism is based on constructive interference, which means you have to be able to deal with the phases in some way. And unfortunately, in practice, we don't know anything about phases. You know, the global ocean is so big. I mean, the waves have a length of 200 meters. You're looking at scales of, say, 20,000 kilometers. So there's no way that we will be able to do that in detail. So you have to follow a somewhat different road. And basically, what we are doing, and that's also how our wave prediction is founded, is we try to get an evolution equation for the ensemble average sea state. Okay, so that's more or less what I can't see. My eyes are not so good at the moment. Yeah, so now most of the time in the open ocean, waves are fairly, to good approximation, linear and independent. And therefore, we can apply what we call the random phase approximation. This means that in a good approximation, ocean waves follow Gaussian statistics. I can give you an argument for that. I can do that online. It's just a blah, blah, blah argument. But we know it just from practice. You know, we've been measuring PDFs of the sea state for many, many years, and they are close to Gaussian. The argument is basically from Klaus Hasselmann. He says, well, if you're in a location in the middle of the ocean, waves are coming from all kinds of directions. So they are generated by different phenomena, like different lows. So when they arrive at your point of interest, that must be independent. And also the fact that you have dispersion is a very good way of generating a Gaussian sea state. Now, but so that's true in a good approximation. But if you look in a bit more detail, then it turns out that nonlinear interactions will give rise to transport of energy inside the spectrum. That means you will get small deviations from Gaussian statistics. And it is these small deviations we are interested in. Because they, for instance, the kurtosis measures deviation from the normal distribution. And it turns out, as we will see in a second, that the kurtosis can be expressed in terms of the equilibrium wave spectrum. And therefore, for a given sea state, we can obtain the probability of occurrence of extreme events. So that's really very nice. It's basically very similar to what we do when we derive the Navier-Stokes equation, say from the Boltzmann equation. You know, in equilibrium we have a Gaussian distribution, and what you do is when you force your system, suppose you have a gold bar, you heat it on this side, then you, of course, you'll get a heat flux, a transport of heat. And when you do that, when you force that system out of equilibrium, that is then the cause of the transport, of course. And the thing is, we can calculate it already since the 19th century. Boltzmann and Chapman and Enskog, they did that. They did it just following. They started with the Gaussian distribution, and they did the perturbation expansion, found the first order corrections, deviations from the Gaussian, and used those first order corrections to calculate transport and viscosity. So, you know, all our theories, the Navier-Stokes equation, is basically based on this type of derivation. And I'm just doing the same thing here. Now, so nowadays, theoretically, it's straightforward to generate fleet waves. As for wave interactions under certain conditions, and basically it's large BFI and small r, will lead to the formation of wave groups. However, as I have to point out, everything depends on the initial phases of the wave, so we have to follow a statistical approach. And basically what we do in wave forecasting is we try to predict, say, the second moment. Because the second moment defined here as a correlation between A1 and A2 complex conjugate, and the ensemble average gives you essentially the spectrum of waves at a certain location. And what we do is we basically follow methods from statistical mechanics, and we have to make two assumptions. So first of all, the following. If you want to derive an equation for this quantity, this second moment, from the Sakharov equation, then it will turn out that you will end up with an infinite hierarchy of equations. It's called the BBGKY hierarchy in statistical mechanics. It's for Born, Bogoliubov, Green, Kirk and Yvonne. So they did it, I think, in the end of the 40s or so. And so what happens, the second moment evolution is coupled to the fourth moment, then you need the fourth moment, you get the sixth, etc., etc. So you have to close, otherwise you will get nowhere. And the way we do that is by assuming that we are close to a Gaussian, and we can make that assumption provided that nonlinearity is sufficiently weak. And so for instance, for the fourth moment, given over here, we can write it, we can break it down in products of second order moments and a remainder which is called the fourth cumulant. And the important property of the fourth cumulant is that for a Gaussian C state, the cumulant vanishes. So that means that if you're looking at weakly nonlinearity, then the fourth cumulant is small and you can approximate it. Okay, so that I've given that example here, just forget about it. So the second moment is coupled to the fourth moment is coupled to the sixth moment, etc., etc. And so that you have to break it down. You have to close it. Now the second assumption I make is that of a homogeneous wave field. That basically means that the correlation function only depends on the distance x1 minus x2, this correlation function. And as a consequence, you can write the second moment in the following very neat fashion. So it's not a two-dimensional matrix, it only depends on one parameter. And capital N is the action density. So then when you take the evolution equation for the fourth moment and disregard the sixth cumulant, then you can solve that problem and you will get an expression for the fourth moment in terms of action density to the third power, and it also involves an interaction function given over here. So it's just an integral over this exponential I delta omega, and delta omega is just the difference in frequencies of the components involved. Now, so when you know this fourth cumulant, then you can do two things. First of all, you can obtain the evolution of the action density caused by four-wave interactions, and you can also determine deviations from normality. Now, if you substitute the expression for this fourth cumulant into the second moment equation, you will get this evolution equation for the action density. And it involves, so three waves are trying to generate a fourth wave, and it involves the imaginary part of the resonance function, which is defined over here, sine of delta omega t over delta omega. And there are two important limits. For short times, this is proportional to time, independent of the delta omega. Then you can show that the relevant time scale is 1 over epsilon square omega naught, which is the Benjamin Fair time scale. And this corresponds to non-resonant interactions, so they happen very rapidly. And then for large time, you can show that this resonance function goes towards the delta function, and this corresponds to the case of resonant wave-wave interactions. But the time scale is much longer, it's 1 over epsilon to the fourth power. And this, by the way, this limit is a limit we usually solve for ocean wave forecasting. But, you know, to be honest, there's also shorter time evolution possible. Now, nonlinearity, both due to the free wave dynamics and to the bound waves, induce deviations from Gaussian statistics. And when these deviations are small, the PDF of, for instance, surface elevation will follow what we call an Edgeworth expansion. So that's a work from 1904, yeah, so that's quite some time ago. And by introducing this variable, x is eta, normalized with the variance, and the square root thereof, then you can obtain for the normalized surface elevation an expansion of this time. So P is an operator working on the Gaussian distribution, and the operator is 1 plus skewness times the third derivative plus kurtosis times the fourth derivative. Yeah, so this is a normal type of expansion, and in particular, kurtosis is important because it will give rise to much fatter tails of the distribution. So I've defined the kurtosis over here. So it's just the fourth power normalized with the second power square minus 3. And if you just work out this in terms of Fourier expansions, etc., and using the expression for the fourth cumulant, you will find an expression for the kurtosis, which is given over here, and it involves the real part of the resonance function. Now, as you can see, this is a very potent thing to solve because, in fact, well, this suggests an 8-dimensional integral, but fortunately we have already a delta function here, so, but we still have to deal with a 6-dimensional integral, which is far too much. I mean, you could do it on your PC at your ease if you have the right code, but operationally we can't do that. So what I went for was for a very simplified approach. I just assumed that I had Gaussian-shaped spectra in the narrow band approximation. Then I could show that this integral would reduce to something of this nature. So the kurtosis is basically depending on the Benjamin-Fair index square, and it also depends on R, which is the ratio of the directional width over the frequency width. And then you also have to realize that there are bound waves, so the kurtosis of the complete wave field will be looking like this. And in the last 8 years or so, people have been doing experiments to study the dependence of the kurtosis on the directional width of the spectrum. And there are 2 experiments, one by Marentek, and I think Miguel was the main driver of this, and also the other is an experiment of the University of Tokyo, and Waseda was the main driver for this. And so the symbols denote the observed kurtosis from the University of Tokyo, and the circles from Marentek. And I've shown you 2 curves based on the theory. One is without bound waves, and one is with bound waves. And as you can see, the one including the bound waves has a fair agreement with observations. So this is basically...
So the difference between including and not including bound waves is whether you calculate with little a or big A. Before or after the canonical
you have to do it in
transformation.
the end with a big A. Yeah?
Well, that's physical, but
Yeah.
little a is where the equations are written.
Yes, sure.
So you
Yeah.
should undo your transformation.
Yeah. Of course. But so it is, you know, people always think bound waves, well, forget about them. I mean, I know someone who's always saying that to me, but I think it still has a bit of an effect here. And of course, in the long run, the bound waves will always be there, so that they, on average, you will see them.
Although we see that one dot exactly on the solid line.
Ah, yeah. Well, ask Miguel. It's a bit of a tricky experiment to do, of course. I mean, it's a 2-dimensional wave tank, and you know, it's certainly not steady state. So, did you do the maximum of the kurtosis, or? And
We
you
do
have
the
to,
maximum of the
and then you have to do the ensemble average because you do many. Yeah.
Well, this is 1 1/2 orders of magnitude of experiment, right? So it's not so trivial.
No. Okay, good. So that's about freak waves. Now I want to talk a little bit about time series analysis, because it's nice to make theories, but you have to be able to compare them in a meaningful way with observations. And the problem was, of course, the thing is that that is bad when you are so long in a field, you start to believe things that you think they are fundamental. And one of the things I believed in, let's say, 8 years ago was...
Can I ask a question before you go on
Yeah,
to this?
yeah.
I mean, you started off talking about freak waves, then you talked about kurtosis.
Yeah.
What's the connection between the two?
The connection is...
I mean, weakly nonlinear analysis and that Draupner wave.
Yeah.
I mean, and kurtosis. How does all this fit together?
Well, the big secret is that the Draupner wave is not so nonlinear as you think it is. It's still weakly nonlinear. So you can describe all those events in the context of weakly nonlinear theory. Otherwise, I would not have been able to get a meaningful comparison between the laboratory data and the theoretical description.
But who says that the laboratory data has freak waves?
Oh, you just look at the time series.
Okay, so we haven't seen that. I mean,
Oh.
I don't know what regime the laboratory
sorry.
data was.
Well, we have to go to the literature or get some other talks of mine from the memory stick. No, I'll show you what you can in detail. You just see this.
But this,
In detail, you just see this all the time. This was done with special preparation to make sure that you had a uniform wave train. But if you start with a wave maker that just generates a signal based, say, on a realistic observed wave spectrum with random phase, then this mechanism is operating all the time.
Yeah, I mean, I agree with Paul. Sorry for talking all the time, but I agree with Paul because he's asking for a prediction. He'd like to say you measure kurtosis, you measure this and that, but we would like to make a direct.
But we do that.
Miguel's going to tell us this, but can I complain a little bit too? Which is,
Good question.
it's great to see this in laboratory that you get freak waves all the time, but you don't get them all the time in the ocean. Of course, you get them occasionally in the ocean.
Hmm.
So I don't want the statistics to be too common.
No. But the statistics are not, the thing is introducing this kind of nonlinear effect will, on average, enhance probabilities by a factor of 2 to 3. So you have your baseline is linear theory, so Gaussian distribution. Of course, then you also get the probability of extreme events.
Yeah, but that's extremely too small, isn't it?
Well, I'll tell you what happens according to me, based on the work I've done, you enhance the probability by a factor of 2 to 3.
I agree with what Walter says, and I think there is a misconception in all of the oceanography. Freak waves and rogue waves are two different things.
Oh,
Really are. You can get freak waves in laboratories. Rogue waves, as Walter says, are very infrequent and they occur in the ocean. The mechanism behind them is very different. And the fact that you're trying to linearize that, it's wrong.
No, well, we have to talk offline about this because you're completely
Yes.
wrong, of course.
okay, so let's keep going, right?
So the way to predict freak waves is very easy. Walter.
Miguel wanted to say something.
Sorry.
No, I just, maybe you want to know the relation between kurtosis and freak wave. Is that the question? Or
Well,
that's
I mean, the question was a bit to start this conversation, right? That to me, a weakly nonlinear expansion that will take you off the probability of a rare event in linear waves to weakly nonlinear waves, that gives you some enhanced probability, maybe a factor of 3.
Yeah.
Mm.
It's not clear to me at all from the talk today that has to do with an event like the Draupner wave or something like that, or that there is not some that captures the physics that went into generating the Draupner wave.
Yeah.
That's
Oh well, there's never a hard proof. There's
Yeah.
never a hard proof of this because it's too complicated. But I can tell you this: I've introduced this kind of system at the European Centre, and so we look every day, in principle, at possible occurrences of freak waves. Now, that's not what I actually. Well, I'm just lazy. What I do is when I hear about an event, like Louis Majesty or Cruiser Dawn, then I look at my map and I see bloom. Oh, big kurtosis there. And really, as a singular event on the whole globe, you just see one dot, and that's where an accident happened. So in this sense, I think, it's not a hard proof, of course, because and by the way, you can never prove this thing anyway, according to Popper. So it seems a reasonable thing.
we have full of experimental data and predictions together. So
Yeah.
I feel comfortable. And
Yeah.
of
The thing
course,
is-
in directional spread seas, the probability is basically linear. That's what Peter has shown. So most of the time you have directional spreading in the ocean, and so the probability is basically the linear.
Yeah.
That's why we don't see freak waves everywhere. Otherwise, would be
Otherwise, you couldn't sail the ocean,
because the ocean is not long crested.
Yeah. I'd be glad, otherwise we really couldn't sail the oceans. Okay, so, but nevertheless, I want to do, so I started and then oh yeah, I of course have been in this field for a very long time, and I've been indoctrinated by the old guys in believing that wave height is really the thing to look at. But to be honest, I described to you how we obtain wave height, and then I realized that this is a bit of a ill-defined way of getting information from time series. So I thought it is better to go back to what I learned at the Department of Electrical Engineering when I was doing my PhD. And that's just using the time series and its Hilbert transform. Just the standard way of dealing with this kind of information. And the reason why we do that in electrical engineering is because the square of the signal is the power. Yeah? And so you're interested in the power. And similarly for our applications on the ocean, you know, you're interested in things like the force and structures. And then it's more likely that you're dealing with something like an energy type of quantity than a wave height, because a wave height is just a visual thing. It has no direct connection in the end with energy. So I'm going to concentrate on the envelope distribution rather than the wave height distribution. So then the thing is, given a time series eta, one would like to obtain envelope and the local phase. And I'm going to show you that this even works for broad spectra, for arbitrary shaped spectra, as long as, say, the first 3 or 4 moments of the spectrum are defined. Okay. So then we all know how this works. At least I've never understood why you needed the Hilbert transform, and then I thought, oh, this is just analytical signals. So then you know that the real and the imaginary part are just connected using the Hilbert transform, and that is basically what we do. So if you have the surface elevation, then the imaginary part of the signal is just the Hilbert transform, and then you can define in a natural way envelope and phase, because this is just a complex number, so you can write it like rho times exponential I phi, and again, and once more, this is eta plus IXC, and then you can immediately obtain from this expression that eta is rho cosine phi and chi is rho sine phi. So you can also infer that needs a little bit more work, but that those two quantities are orthogonal because of the cosine and the sine. And furthermore, that the envelope is just a square root of eta square plus psi square, and the phase of the signal is just arctangent psi over eta. And of course, this is very well known, but in this way we obtain envelope and phase of a wave train. And you know, it's very a general approach. No assumptions on the narrowness of the spectrum, etc., etc. Nevertheless, of course, this kind of method has been used in the context of narrowband wave trains, and then the envelope will be a slowly varying function in space and time. And then in those circumstances, it's customary to introduce just a local angular frequency through this definition. So the angular frequency is minus the ddt of phi. That's just Witham theory. I call this Witham theory. This is what Witham started with in the 50s. Oh, you do not agree?
Witham died this year.
Yeah, I know, 26th of January. Okay, so this is what you would do in a narrowband system. Now, my point is just that we are going to use this notion of a local frequency also for broadband spectra. And so that's just the extension. And people might think, oh, this is crazy. Well, you will see I will get partly crazy results, but I also will get partly beautiful results. Okay. So that's what I do for any time series. Eta, envelope, and phase are obtained from the definition, and frequency is following from this equation, and and we if you're interested in period, it's just 2 pi over omega. And first, a little bit of theory. I'm going to start with linear waves. For linear waves, we have a Gaussian distribution, and I'm interested in a fairly fancy PDF, namely PDF of surface elevation, its time derivative, and similarly for the Hilbert transform and the time derivative. So you have a PDF of 4 parameters, but they are all linearly related. So that means that they are all Gaussian. So you can write down the PDF for that system. It's given over here, where sigma is the covariance matrix, and that's basically it. Now, so we know that eta and psi are orthogonal. So that means that this correlation matrix simplifies considerably, and I've written down all the finite elements over here, where using stationary spectra, you can connect those moments with the moments of the spectrum. And I need moments up to M2. Yeah, so if you have this, then you can determine the determinant of the of the matrix. And it looks like it's given over here. And then you will get your joint PDF of those 4 parameters. It's given over here. Then you have to do just 1 or 2 small steps. First is that from here you want to have the joint PDF of rho and phi, rho dot and phi dot. And you do that by the usual transformation rules, and it's given over here. And then, for instance, this is very nice and interesting PDF, which has lots of interesting properties. But I'm just concentrating here on the case. I'm interested in the joint PDF of envelope and period. So that means I have to concentrate on rho and phi dot, and I have to get rid of the other 2 parameters, and you do that by integration. And that the result of that integration is given over here. And then you normalize things a little bit. This is a normalized envelope, and this is normalized period, normalized with 0 and first moment. And then you get this as joint PDF of envelope and period. A very simple formula. And there appears 1 important parameter in the width parameter, which is defined over here. It's nu. It's m0, m2 over m1 square minus 1 and the square root thereof. And my idea was just to see, well, this is very nice, and I want to see whether this formulation still also works for broadband spectra. So I just did the Monte Carlo simulations. But before that, I would like to note that first of all, the envelope is always following the Rayleigh distribution. So if you integrate over the period, you will get the envelope, the Rayleigh distribution for the envelope. You can also get a marginal distribution law for the period itself. This is just by integrating the PDF over the envelope, and you get something like this. So all this is known. Okay, so Monte Carlo simulation. So I just generate my complex signal in this way. And if I know the complex signal, then of course the signal itself and its Hilbert transform are really trivial to obtain. And I do that on a certain wave number grid. Let's just not go into the details because I don't have so much time. So the surface elevation is then the sum of z plus z star. Then the Hilbert transform is given by this. It turns out to be z minus z star. And you know what I find quite remarkable is that the signal and the Hilbert transform are very similar to the canonical variables of the Hamiltonian formulation.
You said something that went by fast. Are you doing this for, you're also decomposing in wave number as well, or no?
Yeah. Well, no, I do
You have a
time
K at
series.
the bottom, but you don't have Ks until then. So.
Oh, I'm fairly sloppy. But what I do is I do it for a general case, but I just choose x equals 0. So I just get a time series, but I do it for, you know, two-dimensional. Yeah. So because that's what actually happens. What we usually have is time series, and so, but it's from a two-dimensional problem. Yeah. Okay. So now, of course, you can't see this. These are two cases. This is envelope for a narrow spectrum and for a broadband spectrum. And this is period or frequency for a narrow band case and for a broadband case. See, for narrow, it's fairly smooth, so you might think that the period has meaningful interpretation.
Could you turn off the overhead lights for this picture? You're right, I can't see anything.
Yeah, I know. I don't understand because here it was quite all right.
I think if you risk one of those buttons, you might do it. Front,
Excuse me?
Front, front light.
Yeah, down light, wall light,
No, the other on the side there.
off, on, off, and
Front.
on. Oh, okay.
One
No.
next to it.
Oh, this is on air. Oh, of course we are on air. Oh yeah.
Can you turn your laptop around? We're not that far.
Nah,
It's Harvey will be
Brutal
able to see.
about this, main lighting.
but Harvey, I can show you. You're in my office, so we can.
All right.
Yep.
Go ahead.
But anyways, I don't understand. You know, on the screen it's much better than. Anyway, but you can see that this is really very erratic. You know, in the phase jumps and it's a fairly complicated, messy thing. But then, if you next look at the PDF of wave height normalized and period, there you see that looks very reasonable. And this is, say, the numerical from the Monte Carlo simulations. This is from the theory. And you see there's very good agreement. I can tell you that because my software to plot it, if the curves are very close together, it will always put the labels at the same location. So this is narrow band, this is broad band. So that means, to me at least, I was satisfied by doing this exercise that it is a very good idea to just use the Hilbert transform and the signal itself to do the analysis. And life is very simple then.
The other on.
Oh.
Is that too? Never mind, that's good. Looks good.
Yeah. Okay, and this is a comparison between the marginal distribution laws for the envelope and for the period. And you should see in each graph two curves, but it is very difficult to see the difference. So, you know, that just was for me very convincing that this kind of approach works. And so that's what I've been using. Now, a very brief sketch of extension into the nonlinear regime. So I have this weakly nonlinear approach, and I just use the ensemble of a single Stokes wave. And surface elevation is given over here, up to third order. You need to go up to third order in order to capture the kurtosis properly. And now this nonlinear wave has, of course, things like skewness and kurtosis. And I've worked out what you do is you start with the characteristic function of the PDF, which is basically the Fourier transform of the PDF of an n particle, an n body PDF, and then from there you start doing the theoretical development, and it's too elaborate to discuss it now. But what you find after a bit of work is you find for the envelope the following extension of linear theory. So the PDF is again Rayleigh, but there is a correction factor which involves the skewness square and the kurtosis. And rho is normalized envelope. And basically what I want you to show is I'm using the actual time series to simulate events. And I do that on purpose for very steep waves. Something like steepness of 0.15 is really steep. We never see that in nature. And then I can show you how well that theoretical, this formula is comparing to the Monte Carlo simulation. And that's given over here. So number of lines, this greenish line is the result from the Monte Carlo simulation. Then this line is linear theory, Rayleigh distribution. And the black line is, forget about the blue line now. The black line is the result of that formula. And you can see that over a decent range, we have a good agreement with the numerical simulations. So this approach, although it's a silly, weakly nonlinear theory, is doing pretty well.
So can you tell, it's Monte Carlo simulation of what now?
Of this system. So I take the
So
formula.
there's no wave dynamics in it.
No,
It's just that.
this is just for the bound waves.
Okay.
Yeah. So I just do this formula and I generate, I take a Rayleigh distribution for the amplitude, random phase, and then do it 5 million times. Because that's what you need. Because the level of probability is quite low, I talk to up to 10 minus 5. Yeah. So you need at least 100,000 events to do something. And I can show you that's sensitive. This was to upset all the ensemble people at the European Weather Center. We do lots on ensemble weather prediction with 50-member ensembles. And people claim that you can do extreme weather with such a system. And my claim is that if you only have 50 members, you will never do an extreme event, of course. Only with a probability of 2%. But of course, never with a probability of this type. So just to tease them, I show them what happens if you go, instead of from 500,000, you use 5,000, then you see you get a lot of rubbish. Yep. So that was just to tease them.
The horizontal axis is A, basically.
What do you mean by A? It's a normalized, what is it, the envelope.
Envelope amplitude.
Yeah. Okay. Okay, that's basically it. I mean, it's 1 hour. Now I can rest, I hope. So, questions?
Our speaker very hard. Are there any other questions for him?
Didn't Tayfun write a paper in 1986?
Who?
Tayfun, T-A-Y-F-U-N.
Typhoon.
Excuse me.
Yeah.
Where he looked at the statistics associated with random weakly nonlinear
Yeah.
waves. Have you compared your theory with what he found?
Yes, of course.
And they agree?
Well, he had a few small errors, but that's not so bad. So he did the theory just for what we call the bound wave part of the.
But didn't he allow for modulations as well? Or?
No.
He took into account only quadratic nonlinearity, and this is fundamentally incorrect. So to
Wow,
put it,
that's boo. No, but he, of course, it was a very good thing what he did. He was the first who realized that you can do things like that. That you can do Monte Carlo simulations, and he came with an approximate description. So yeah, that was good. But of course, we need a little bit more. Yeah.
Very good. Let's thank our speaker again.